Hey, welcome back to our journey learning 6502 assembly on the Apple II. Today we talk about shift operators and logical operators. That's quite an important topic, very useful. So let's start with the shift operators. So a byte is a sequence of 8 bits, each one with values 0 or 1. And when we do a shift, basically we shift that entire pattern either towards the left or the right. So we can see here this example in the assembly lines book. If we do a shift left, basically we are moving all the bits on the pattern to the left, of course. So if you start with the value hexadecimal 00, which in binary would be just basically all zeros for all the bits that are part of your byte, and then you shift them all to the left, of course the result is the same, right? You still have all zeros. If you had all ones, the result is going to be slightly different, as we're gonna see. So let's take another simple example. So if you have 0, 1, hexadecimal 0, 1, that's a sequence where only one bit is flipped. One bit has the value 1. That means that this has the overall value of 1. The result, when we move the bit, right, we shift it from the end position and we shift it towards the left position. Now we have hexadecimal or decimal 2 as a result, because a flipped bit on this position basically means this has the value of 2. So you can see that basically what we accomplish by doing a shift left is multiplying the number by 2. So if the bit is here on the 1 position and then it moves here, then we have the value 2. If it were to move 1 position more to the left, then we have the value 4. If it shifts once again to the left, we have the value 8, and so on and so forth. So by doing shift lefts, we can multiply a number by 2. So we are also interested when we are doing shift lefts, we might be dealing with a couple of bytes instead of a single byte. So we also have the carry flag being properly flagged here. So if you happen to have a 1 on the leftmost bit and you do a shift left, that bit becomes it gets the value of the bit that we have on the other side, and this bit basically shifts out of our byte and into the next byte, and this is accomplished by setting the carry flag with value 1. And also we have the 0 flag being set appropriately. So if you have a result that is basically all zeros, like you see on this first row and also on the third row, then the 0 flag is set to 1. And here we have a new flag, that's the sign flag. The sign flag is used to indicate whether the leftmost bit is 0 or 1. And this is actually used because when we want to represent negative numbers, what we do is we use the last bit, the leftmost bit. We use it to basically represent whether the number is positive or negative. We haven't used it yet, and we're not gonna use it soon, but it's interesting to know that's how we represent negative numbers and that there is a flag that's associated with that. So that said, let's take a look at an example of doing a shift left. So I have put together an example program here. This is not part of the assembly lines book. And what we do here, I will come back and explain these constants that we are defining here later. So this routine, basically what it does, we print a header, and that header is this thing here. that we're saying yeah, basically it's a string with val res as in result. So the original value, the result of the shift left, the whether the carry flag, sign flag, or zero flag are on or off. And then we have for each example that we have here on the assembly lines book, we have an equivalent practical example here. So we print this header, and then we load the accumulator with all zeros. Then we shift left that thing. And this shift routine actually not only does the shift itself, but it also captures the state of all the flags, the carry flag, the sign flag, and the zero flag, and it stores them in certain memory addresses. And basically what's put here in these memory addresses, we have the original value that we shifted, then we have the result of the shift, then we have whether the carry sign or zero are set or clear. And here we use basically a 0 or a 1 to represent set or clear. So the shift routine stores all these values in these memory addresses. And also at the end, this shift routine does a print row, calls the print row subroutine, which will print one of these rows. And the print row routine, we load the accumulator with the original value and we print it. Then we print some spaces to separate it here. Then we load the result and we print the result. And then for each one of the flags, we print either on or off. And you see here we have something new. It's a bit of an if-else pattern. And this is how you do it in assembly. So we load the contents of the carry address, which basically is going to have a 0 or a 1, depending on whether the carry flag was set or not. And then we compare that value with set, which is 1. And then if the carry flag is set, which means that this comparison operation resulted true, then we branch to this label. That means that the carry flag is on, which basically we print the string on. There is a separate routine that basically prints this string plus 2 spaces to the screen. And then we follow on to the rest of the program. However, if this comparison yielded false, basically we're not going to branch here on this carry on. We are going to print off, right, because it's off, and then we jump to the next step, which is the sign flag. So you see that we never, there is never a situation where we go both here and here. It's an if-else. So the combination of this BCS with this jump and this the combination of this branching with this unconditional jump is what gives you this if-else pattern. And there's also something else interesting about this program. So if we go to any of the routines that print a string, for instance, this print on, which basically prints the on string plus two spaces, we are not anymore checking the length of that string. What we do is we already know this pattern, right? We put 0 on the X register, and then we put the accumulator with the contents of basically the address on with an increment of X. So we start with 0, then we start exactly on the address pointed to by on, which means we start on the first character of this string. And if that thing is equals 0, which is basically the end of string marker, you can see here that I have added to the end of the, we have the string, and then at the end of the string, we have this basically a byte with 0, and that's the marker that the string has reached its end. So we check if the contents of the accumulator are equal 0. So if the character is 0, then basically we go to the end and we we don't need this. So we leave this print subroutine, it's over. However, if the character is different than 0, then we print the character to the screen and we increment x, right? So this expression, next time we loop, it's going to point to the next character. And if the result of the increment is also that we have gone over 255 and we are back to 0, we have sort of overflown the X register. We also, unless we have overflown, we go back to the loop. So this guarantees that we can print strings up to 255 characters. So we stop either when we have a 0 or when we are over 255 characters. And this is the string, and this is 0. And you can see a similar pattern that I have used for the other moments where we print things. So let's assemble this program. You can see already I had a previous execution here, but let me run it again. Yeah, if you go now and you compare to the values that we had on the assembly lines book in the off and on, we can see that this works. Also, we can use this as a vehicle to try out stuff. For instance, I told you that if you have a pattern like this, you have a pattern where you have the 1 here and you do a shift, then you have 2 as a result. So you start with 1, and because this bit basically flips to here, instead of 1 we have 2 as a result. So let's try something different here, and let's start with 2. So when we do a shift left of a byte that has the value 2, then it will have the value 4 because it multiplies by 2. Let's see the result. Yeah, you see we started with 2 and then we landed on 4. So you can see this happening here. So similarly, we have the shift left. You can expect that we also have a shift right, which has precisely the opposite effect. So it divides by 2. But instead the shift left, it's called arithmetic. So arithmetic shift left, ASL. And the shift right is a logical shift, so it's logical shift right. This is really about details about how it works internally. But what you have to bear in mind is that one is called ASL and the other is called LSR. So we can see an example just by going to this program. We can change the place where we do the shift left. Now we do let me recall that, it's LSR. I actually repeat the shift a number of times here because some of these flags, they get cleared by our code that's printing things to the screen and storing things. So it's easier. It was easier to repeat this, to load the original value and do again the operation. But if we change in these 3 places, we have changed our shift from left to right. And here we can see the results. For instance, I told you that if you do a shift right, you divide by 2. So we started with the value 2, and now we have the value 1. And we have the carry sign and 0 flag set accordingly. So let's try now having a 4 and dividing it by 2. So we have a 4 and we do a shift right and we land on a 2. And if we have an 8, we should have a 4 as a result, right? If we start with an 8 and we do a shift right. Yes, we start with the 8 and then we land on the 4. So you can see this is quite an interesting program that you can play around a bit with the shift left and right operators. You can also play with the rotate instructions. So rotate left and right, they are very similar to the shift, but the difference is that the bit, you remember that when you have 1 on this bit here and it shifts left, it shifts sort of out the byte, then its value goes into the carry flag. But if you do a rotate, what happens is that that value that kind of falls over the edge of this side actually lands on the first bit on the other side. And if you do a rotation right, you basically do the opposite. So the bit that is here, when it kind of falls over the edge, it actually lands on the opposite bit. And yeah, we saw that in the shifts, this gets this edge bits get assigned the value 0 when they kind of fall over the edge. So that's it about the shift operators. And now we need to switch gears and talk a little bit about the logical operators, which are also quite interesting. So, logical operators. We have basic logic operations that are and, or, not. And actually not, we have two kinds. We have the kind of normal OR, and we have the exclusive OR. So we use 0 to represent a false value, and we use 1 to represent a true value. So you can see how we only need 1 bit to represent a value that's a Boolean value, a value that can only be either false or true. And this is useful for a number of things. Basically, we want to know whether something is or isn't, right? So for instance, the 0 flag, we want to know whether the accumulator is 0 or it's something different than 0, whether the question is the accumulator 0 is true or false. It can only be either one of true or false, and then we can represent this with a single bit. So if we take a single bit and we say, we take the AND operation, that means that both the bits must be true, otherwise the result is false. So if you say 1 and 1, that results in 1. So both are true. If both are true, then the answer of the AND operation is 2. I'm sorry, it's true, means it's 1, the number 1. So if you say if one thing is true but the other thing is false, the result is going to be false because both of them need to be true in order for the result of the AND operation be true. The OR, on the other hand, it's insufficient that one of them is true. So if you have like a regular OR, it doesn't matter if either one of the two is true, the result is going to be true. So you have a variation which is the exclusive OR, and the exclusive OR, you're basically saying if one and exactly one of them is true, then the result is true. But if both are true, then the result is false. They're basically saying it's either one of them and exactly one of them must be true in order for the exclusive OR operation to be resulting true. And not, basically, it's in the inversion of whatever. So if you have false, the opposite of false is true. And if you have true, the opposite is false. So this one, we're not gonna deal with it today. We are going to learn about the AND and the or and exclusive or operators. And also we're going to learn about an operator called bit that allows us to determine the value of a specific bit inside a byte. So I explained the principle of how you compare a single bit, but the instructions of 6502, they apply to an entire byte, right? So the entire byte, we are doing an AND. So what happens is you start with a byte. Let's say, I'll just make this up. So you start with this byte. So this is your first value, and then you are doing an AND. Let's say this is what you have in your accumulator, right? So you have this pattern, and then you do an AND with the value with this value. So what happens is that we do the resulting AND bit by bit. So we take this first bit here, 0, and we do 0 and 0. I mean, if either one of them is 0, it's always going to be false. So we can already say that all these bits are going to be false, right? Because if it's 0 in either the top byte or the bottom byte, then the result is always going to be 0. So you see that it really, because we see 4 zeros here, it really doesn't matter what's up there. It's going to land on 4 zeros here. And because we have 3 zeros here, we also are landing on zeros no matter what's up there. And here we have a case where both of them are true. Both of them are 1. So the result of the AND operation of this bit ended to this bit is this result. And you can see here basically one, I mean, of course, we can use the AND operation just to perform logical AND conditions. So we want two things to be true in order to, I don't know, go to a certain branch or take a certain decision on our program. That's, of course, one way that you can use this. But the other way that you can use this is basically to single out one bit here that you wanna kind of filter through, right? So let's say you have a byte where you have, of course, 8 bits, and let's say that each one of these 8 bits represents a different boolean, a different true or false variable on your program. But at some point you only care about one of them. You want to sort of extract that the value, whether it's a 0 or 1 of that specific thing. Then you can do an AND operation using a mask like this, where you only put 1 on the bit that you care about, and then you get this as a result. So this is how the AND operation works. So let's see a practical example of that. Okay, so we have here another exercise to exercise the logical operators. We're going to start with AND. So we have two values, and we're going to do value 1 and value 2, and store whatever is the result on the result memory address. So here we load value 2, and value 2, it's basically a mask that has the bit 1 set on this particular bit. And then we have value 1. And we do here AND between value 1, which is in the accumulator, and value 2, and store the result, and then print the result. And this print result basically shows value 1, and then prints the string AND, value 2, string equals, and the result. And also you see a funny little bit here. It's literally a bit. So we are going to talk about this later. We can actually, for now, just comment out this part. We don't need it. So it's what I explained to you. We're going to show value 1 and value 2 equals result. So here you see that we had this, start with this value 1, which has 4 bits set to 1. But then we do an AND with this guy here, and only the bit that where both of them are 1 are going to fall through. So that means the result is actually equals to this sequence here, right? Because it's all the others are zeros, and if this one is 1, then we have a 1 here too. So that's how the AND works. So you could say things like I do an AND between two. So an AND between true and false is going to be false. And an AND between true and true is going to be, of course, true. Now, if I want to simply check the value of a single bit, so let me go back to that pattern that we had here. If I just want to check this, whether this bit is 0 or 1, there's another way that we can do that using an operator called bit. And this is the part that we just commented here. I'm going to show you what happens. So I start by loading the mask. So this is our bit mask. I put it in the accumulator. And then I call the instruction bit with value 1. Basically, we're going to apply value 1 to this mask. And if one or more of the bits that are true on this mask, they are also true on value 1, so they are set, we set the 0 flag to 1. And if the bits that we indicate with 1 here on the mask, they are 0 on the value that we're checking, then the 0 flag is going to be 0. So we here have that if-else pattern again. So if the result of the bit operation made the 0 flag to be containing 1, right? So it's got not equals to 0, then we jump to this true part where we basically print the byte with value 1 to indicate true. Otherwise, if we did not make this branch instruction, we print the value 0 to the screen. So we put 0 on the accumulator and jump to this address, we print 0 to the screen, and it's done. So you can see here, for instance, if we have this bit mask, right? This is actually value 1. We could value 2. We could even say the mask is value 2, and this is the value to test. We do this operation, so this bit here is the bit we care about, and it is 1. So we expect that the result of this bit operation is going to set our 0 flag to 1. So it's going to print 1 on that last character. Yes, here's the 1. However, if these things become 0, now we expect 0. We expect a false. Yes, so bit accomplishes kind of the same that you can with AND when you want to check for a certain bit whether it's true or false, but it has the advantage that it doesn't touch the accumulator. So AND, it basically takes two values and puts the result in the accumulator, while this bit operation is going to only test and set the 0 flag. So no, the accumulator doesn't get touched. So this is for the AND operation. What about other operations? So the OR is OR accumulator. So if you wanna, this bit thing, we don't care about it for this example. We are only checking the logical operator OR. So we see here, if we say, I want to do an OR between 0 and 1, right? So this is 0, this is 1, and I do an OR between the two. So true or false equals true. If both are true, it should remain true. So true or true equals true. But if we change this to an exclusive OR, that's how you say it, an exclusive OR, EOR. Now the result is false, because actually only one of them may be true, because it's an exclusive OR. Yes, so this is exactly what we expected. So now we covered both shift and both shift and logical operators. And that is what we had for today. I hope you have enjoyed it, and looking forward to meet you for our next episode. See you.